Hello everybody, getting ready to do lesson 6.2 part 1 of pre-calculus math today, the classwork version of law of cosines. This is my email to contact me for materials. Okay, today's lesson has 6 points here of notebook taking. So have your notebook out or have a notebook guide for that. And then 52 points here on your classwork sheet, students. You should have your classwork sheet in front of you. If you need classwork sheets, email me for those. And teachers and students, we start out with a bell work like we always do. In these exercises, evaluate the expression without using a calculator. For this one, arcsine of the negative square root of 3 over 2. Evaluate those without a calculator. And teachers, give your students about 3-4 minutes for that. Okay, teachers and students, you should be finished now for our solutions for today's bell work. Arcsine of negative 1. So the arcsine of negative 1 would be the same thing as negative pi over 2, which would be going this way on your unit circle, because sine of the negative pi over 2 equals negative 1. So that would be here would be negative pi over 2, because sine of negative pi over 2 would equal negative 1. And then down here, arcsine of the negative of square root of 3 over 2. Arcsine of the negative square root of 3 over 2 equals the negative of pi over 3, because sine of negative pi over 3 equals the negative of square root of 3 over 2. So you just go into these because of its situations. If, because, if, because, if, because. Okay, into our lesson today, students, into your notebook, page 1, your introduction here is 6.2. Two cases remain in the list of conditions needed to solve an oblique triangle, such as side, 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 and side angle side, SAS. To use law of sines, you must know at least one side and its opposite angle. When you are given three sides, side, 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 or two sides and their included angle, side, angle, side, none of the ratios in the law of sines would be complete. In such cases, you can use the law of cosine. So there are cases here where cosine will help you solve triangles. Page 2 in your notebook, law of cosine, standard form, and an alternative form. So we have this situation here, a squared equals b squared plus c squared minus 2bc cosine a. That would be your standard form of finding a triangle here, finding a side here. And then the alternative form of this will be using the angle of cosine a would equal b squared plus c squared minus a squared all over 2bc. That would be an alternative form of this situation here. Whichever you find would be simpler. And then b squared, again, you have a squared plus c squared minus 2ac cosine b. So we're using cosine here. And then take the cosine of b, you'd have a squared plus c squared minus b squared over 2ac for that one. And then c squared would equal a squared plus b squared minus 2ab cosine c. And then we do that again over here. The cosine of angle c would equal a squared plus b squared minus c squared all over 2ab. So this would be your law of cosines. Okay, let's go into an example 1. Three sides of triangle SSS, side, side, side. Find the three angles of the triangle shown. So we have our three sides here. We have SSS. It is a good idea first to find angle opposite the longest side. So that would be, it looks like, or maybe it will be this one here, or B. I think, yeah, this is your longest side. So it'll be angle B, side B in this case. Use the alternative form of the law of cosines. You find that cosine b, so the cosine of b here would equal a squared plus c squared minus b squared over 2ac. So we do our plug-in here. We plug in for our values here, and we get this would equal cosine b. So when we crank that out, we will get a negative 0.45089. Because cosine B is negative, you know that B is an obtuse angle given by B, in this case, will be 116.80 degrees. At this point, it is simpler excuse me, to use the law of sines to determine A. So now we can switch to law of sines. Now that we have one angle here, we have angle B here, which is sine 116.80. So, and then we have our side here of A. We know A and we know B. And so to find sine of A, we go with our plugins here, and we come out with 0.37583, and then we can determine the angle from that. You know that A must be acute because B is obtuse, and a triangle can have at most one obtuse angle, so A would equal 22.08. So when you do your inverse on your calculator, you find it this equals 22.08 degrees, and now we can find our other angle here. 180 minus 22.08 minus 116.80 equals 41.12. Okay, starting into this guided practice here, using the law of cosines. Use the law of cosines to solve the triangle. So here are our given lengths here of our sides. We have 12, A is 12, B is 16, and C is 18 here. So we need to solve for these angles here. Angle A, C, and B is what we need to do. So from that, we're given this. So we can start with a cosine here, a law of cosine setup here. So we go B squared plus C squared minus A squared in our numerator for our to find the cosine of A, to find the angle measure of A over 2BC. That is our formula there for that. And then when we fill in our values from our given, we can 16 squared, 18 plus 18 squared minus 12 squared all over 2 times 16 times 18. We get a number here. And then when we use our inverse cosine function on our calculator, we get 40.80 here for A, is what we'll get for A, is 40.80. And then once we have our angle measure here for A, we can build off of that down here. For sine B, to solve for this angle here, we go B sine A. We know what A is now, and we know what B is, and then A, we know what A is as well. So we can plug in here to find what our sine of B is. So this number here, when we plug in for these values here, we come up with this for our number from this calculation, and then we use our inverse sine, and then we get 60.61 for B. So we know this angle measure. Then we can just subtract to find what our angle C is. Our angle C is 78.59 degrees for C. So that'll be your methodology here to use the law of cosines to solve a triangle like this. Okay, back in your notebook, page 6. Do you see why it was wise to find the largest angle first in example 1? Knowing the cosine of an angle, you can determine whether the angle is acute or obtuse. That is, if cosine theta is greater than 0 for 0 less than theta less than 90, it is acute. So if cosine theta is greater than 0, it's acute. And then if cosine theta is less than 0 for 90, less than theta, less than 180, it's obtuse. So in example 1, once you found that angle B was obtuse, meaning it was up here, it was less than 0, you knew that angles A and C were both acute as well. Furthermore, If the largest angle is acute, then the remaining two angles are also acute. So here's another very important tidbit here in solving triangles. Okay, going into our next example here, example 2, two sides and include an angle, which is side angle side. Find the remaining angles and side of the triangle shown. So we have side, and then we have angle, and then we have side here. Use the law of cosines to find the unknown side A here in the figure. So A would be A squared equals B squared plus C squared minus 2BC cosine A would be your expression here to solve for A. And then we plug in from our figure up here, and we get this expression here to solve for A. Then A squared will equal 29.2375 from this amount over here. And then that will equal, when you take the square root of both sides, you have 5.4072. And then because A equals 5.4072 meters, you know the ratio sine A over A. And you can use the reciprocal form of the law of sines to solve for B. So sine B over B equals sine A over A. So therefore sine B will equal B sine A over A from this expression here, solving for sine B. And then we plug in from the values that we know. Sine B will equal 9 times quantity sine 25 degrees over 5.4072. Sine B will equal 0.703. And then knowing that, there are two angles between 0 and 180 whose sine is this 0.7034. Now B1 will equal 44.7, and that would be this here, will equal 44.7 degrees, and B2 would equal 135.3 degrees. So which one is it? We have to ask. For B1 equals 44.7 degrees, our C1 here would be 110.3. And for B2 equals 135.3 degrees, to find C2 in this scenario here, C2 would equal 19.7 degrees. So because side C, which is here, is along the side of the triangle, C must be the largest angle of the triangle. So B will equal 44.7 and C will equal 110.3 due to this reasoning here. Okay, let's try one. Using the law of cosines. Use the law of cosines to solve this triangle here. And what do we know? Side angle side is what we know here. Okay, so in our next guided practice here, use the law of cosines to solve this triangle here. And then our givens here, side A is 10 millimeters, side C is 15 millimeters, and then this side C here, and then our measure of angle B will be 20 degrees. So that's our given here. So using our law of cosines to find B, see side B would be over here. To find that side there, we use this B squared equals A squared plus C squared minus 2AC cosine B. And then so our plug-in here would equal 100 plus 225 minus 2 times 10 times 15 times cosine 20 degrees. So this is what we need to calculate right here. And then this comes out to 43.0922. And then when we convert this into a length here, B would equal 6.56 millimeters here for the length of angle B here. We take the square root of that. So knowing that, to find cosine A, which would be this angle measure here, we need to find this angle measure here. Cosine A would be equals to b squared plus c squared minus a squared over 2bc. So when we plug in our values here that we know, we have this, then over 2 times bc be 6.56 times 15. 2 times 6.56 over 15. And then when we calculate that, we come up with this number here, and then when we convert that into an angle measure, we get 31.40 degrees for A here. And then we subtract both these angles from 180, and we get 128.60 degrees for the measure of angle C here. Okay, going into our next example, example 3. An application of the law of cosines. So a pitcher's mound on a women's softball field is 43 feet from home plate. So it'll be 43 feet here from home plate. And the distance between the bases is 60 feet. So we have 60-foot baselines here as shown. The pitcher's mound is not halfway between home plate and second base. So it's not halfway between here and here. It's not quite halfway. How far is the pitcher's mound from the first base? So we want to know this measure here. So in triangle HPF, H is 45 degrees. This is our 45 degree angle there. Line HP bisects the right angle, so our line HP here, but we have a right angle here, so that's what makes this 45 at H. So F equals 43, here's our 43, and P equals 60, so we know that much. Using the law of cosines, for this SASK of h squared, which is our h squared here, equals f squared plus p squared minus 2fp cosine h, which is our law of cosines. And then when we plug in our values that we know, for f squared would be 43 squared, then p squared here would be 60 squared minus 2 times fp would be 43 times 60, and then cosine of h here would be 45. So we substitute in our values, and then we come up with this number here. So the approximate distance from the pitcher's mound to first base is the square root of 1800.33, which is 42.43 feet. So it's about 42.5 feet here on this distance here. Let's try one now. To approximate the length of a marsh, a surveyor walks 380 meters from a point A to point B. So point A to point B. Wait a minute, here's point B, point C. I guess this is point A here. So 380 meters from point A to point B. Then the surveyor turns 80 degrees and walks 240 meters to point C. So then he walks over here. Approximate the length of AC of the marsh. So we need to find this length here, AC. So to do that, we can make a triangle here. We got this triangle here. Here's our 80 degrees here that we turn. Here's our turn here. We have a straight line, and then we make a turn here 80 degrees from that straight line. Then we walk over to C. So angle at B, so the angle here at B here, we have 180 minus 80 would be 100 degrees. So this is a 100-degree angle here. B squared equals 240 squared, 240 squared. So we have 240 over here plus 380 squared minus 2 times 240 times 380 cosine 100. And we know this angle here. So using the law of cosines, after we crank this out, we're finding here b squared, which is the length here. So that equals 233.673. Whoa, 233,673.4. And then when we take the square root of that, we get 483.4 meters for the length here of B. Okay, moving into our next example here, example 4. In application of the law of cosines, a ship travels 60 miles due east. So we have 60 miles here due east. Then adjusts its course northward. After traveling 80 miles here in the new direction, the ship is 139 miles here from its point of departure. Describe the bearing from point B to point C. So we need a description of that. You have A equals 80. Here's our A. It's the opposite of this angle here. Here's our A. B equals 139, so it's opposite of this angle here, 139. And then C, or angle C, using an alternative form of the law of cosines, you have cosine of B equals A squared plus C squared minus B squared over 2AC. We have C here equals 60. So we're trying to find, see, cosine B here, this angle here. Do we have cosine B? We don't. All we have here are measures of the sides. So we're trying to find angles here. So this is the alternative form of the law of cosines. We have our side lengths. And then we plug that in, substitute for A, B, and C, and we have that. And then we come up with negative 0.97094. And this is for B, so you take the arc cosine of this number here, and you get 166.15 here for B. So our angle measure here would be 166.15. Therefore, the bearing measured from the north from point B to point C, we have a 90 here. Let's see, 166 minus 90. Okay, 166.15 minus will be 76.15 for that angle measure there. For the measure here of angle B. Or north 76.15 east. So it's going north by 76.15 degrees east there on that one. Take a 90 here, and then you get this measure here. Okay, let's try one now. So on a map, Minneapolis is 165 millimeters due west of Albany, and Phoenix is 216 millimeters from Minneapolis, and Phoenix is 368. Here's Phoenix from Albany. So we have this triangle here, and so we can also use this measurement here. We got a right angle here written here, 59.7 to this side, and then 72.8 degrees to this side here. And then we have our side lengths here, and we have a side length here for that. So we should have everything we need. 368 here on this length. And then this would be 13.1. 13.1. for this measure here, 13.1 degrees. Okay, so knowing that, find the bearing of Minneapolis from Phoenix. So knowing the information that we have, again, here is our beginning diagram for that. And then we plug in our values here. A equals 165. B equals 216. And then C equals 368. So cosine B here would equal 165 squared plus 368 squared minus 216 squared over 2 times 165, 368. And then we get this number here. So B, when we convert this into angle measure, will be 17.2 degrees, which is, I think that measure right there, 17.2 is here. So B, angle measure B, will be 17.2. And then when we crank this out for cosine A, which is this measure here, we get 13.1 for measure A there, 13.1. And then find the bearing of Minneapolis from Phoenix. So to find that, we go north 90 minus 17.2 minus 13.1, and then we get north 59.7 degrees east. Find the bearing of Minneapolis from Phoenix, so we get this number here. We subtract 17.2 and 13.1 from 90, and then we get this number here. And then down here, find the bearing of Albany from Phoenix, so we get north 90 minus 17.2, and we get 72.8 degrees east for a bearing of Albany from Phoenix. And that is your lesson today, 6.2 part 1. If you need solution PowerPoints, you need classwork sheets, you need homework sheets, email me here for those. Thank you very much.